Hi folks, in this video we're going to look at the topic of motion and we're going to try and fit as much of it as we can onto the one page here. This video is suitable for those who are studying GCSE Physics and also double award physics. There is some content that is higher tier only, and I'll make that clear by using a different colour. So anything that is in black would be both on foundation and higher tier papers, but anything that is in blue will be on the higher tier only. So we're going to start off by looking at what do we mean by a scalar and a vector, and then we'll look at some specific examples. So we'll start off with the difference between a scalar quantity and a vector quantity. All physical quantities can be split into these two groups. Scalar quantities are ones that have size only, whereas a vector quantity is one that has size and direction. Now we're going to look at some of these scalar quantities in turn and then look at their vector counterparts. First up, we're going to look at distance. So distance is just a way of saying how far something has travelled. We always measure it in metres. Now it doesn't give us any indication of the direction in which we've travelled, it just tells us how far we've gone. So we're going to look at an example here. We have a rectangle and there are four corners, A, B, C and D. So let's say that we were to start at A and we were to travel all the way around the perimeter of this rectangle and finish up at D. So we travel from A to B, we travel from B to C, and then from C to D. The total distance travelled would just be the sum of each of these individual lengths. So total distance in this case would be the 20 metres from A to B, plus the 10 metres from B to C, plus the 20 metres from C to D. And in total, we've travelled a distance of 50 metres. Displacement, on the other hand, because it's a vector quantity, it has a direction associated with it. So displacement is how far you've travelled in a given direction, which means that it doesn't really matter that we started at A, travelled to B and then C and then D. All that really matters is where we started and where we finished. So another way of thinking of displacement is that it's the shortest straight line distance between 2 points, which in this case is the straight line that we get from A to D. So because of that, we can see that the displacement is not equal to 50 metres, it's actually only equal to 10 metres. And because displacement has a direction associated with it, in this case we could say 10 metres south. So displacement, just like distance, is also measured in metres. The only difference being that it's a distance in a specific direction. So next up we have speed. Speed is defined as the rate of change of distance. In other words, it just means how quickly the distance is changing. We measure speed in metres per second. So the equation that we use for speed is equal to the total distance travelled divided by the total time taken. Now because speed is measured in metres per second, it means that distance must be measured in metres and the time must be measured in seconds. Now that's quite a long thing to write out, so generally we'll use symbols instead, and that is S is equal to D over T. So S is speed, D is distance, and T is time. Now typically throughout a journey, the speed wouldn't remain constant, it would change throughout because an object might have to speed up or slow down for various reasons. So what we're actually working out here is an average speed, and that's because we're using the total distance travelled divided by the total time taken. This actually isn't the only equation that we can use to work out an average speed. We can just use the method that you would for anything where you're trying to work out an average, and that is to add up all the values that you have and divide it by the number of values that you're using. Typically, we would have two values if we know the speed at the start and the speed at the end. Well, if we add the two together, we can divide that by 2. So we can write that as the average speed is equal to the initial speed plus the final speed divided by 2. Just be careful when you're putting this into the calculator that you add the initial and the final speed together first before you divide it by 2. I like to put brackets around it to help make sure that both those quantities are added before we divide. So velocity is a similar concept. It's basically speed but in a given direction. We can define velocity as the rate of change of displacement. And it's important just to recognise that when we work out velocity, it is displacement and not distance. It has the same units of meters per second. So the equation that we use for velocity is equal to displacement over time. Again, since velocity is measured in meters per second, then displacement must be measured in meters and time must be measured in seconds. We can shorten this down to V is equal to d over t, where V is velocity, d is displacement, and t is time. I'll just note here that those of you who are familiar with the SUVAT equations, who do additional maths, you may use this equation as V is equal to S over T, where S represents displacement. But in physics at GCSE level, there's no need to know or to use that. If we know the initial and the final velocities, we can also work out the average by adding them together and dividing by 2, just as we do with speed. So next we'll look at something called the rate of change of speed. So the rate of change of speed is just a way of saying how quickly the speed itself is changing. We measure the rate of change of speed in meters per second squared. So to work out the rate of change of speed, we need to know what the change of speed is. So what's the difference between the initial and the final speeds, and we need to know how long it took for that change to occur. So to find that difference in the speed, we take the final speed and subtract the initial speed. Both of these will be measured in meters per second. Time will be measured in seconds, which gives us the rate of change of speed in meters per second squared. When it's velocity that's changing, we don't call it rate of change of velocity, we give it a name, and that is acceleration. So acceleration is the rate of change of velocity. It is also measured in meters per second squared. So acceleration is the difference in the velocity at the start and at the end divided by the time taken. Again, velocities will be measured in meters per second, time measured in seconds, therefore acceleration is meters per second squared. We can shorten this down using the symbols A is equal to V minus U divided by T. So A is the acceleration, V is the final velocity, U is the initial velocity, and T is the time. Make sure you take care when you're writing out the V and the U to make sure that they're very different looking. Sometimes when you're in a hurry, the V and the U can look quite similar, so make sure the U has that little tail on the end. Now, depending on whether an object is speeding up or slowing down, we'll actually find that the value for acceleration can have either a positive value or it can have a negative value. Now, the reason for that is that acceleration is a vector quantity, and vector quantities have direction. Now, a normal convention would be that if an object is moving in one direction, it would have a positive value, and if it's moving in the opposite direction, we would give it a negative value. So in general, things that are moving to the right are given a positive value, and if it's moving to the left, we give it a negative value. So for example, let's say we had an object that was moving to the right with a velocity of 3 meters per second. Well, if it was to stop and then move with the same speed but in the opposite direction, then we would say that it has a velocity of minus 3 meters per second. The speed is the same in both cases because speed is a scalar quantity. Scalar quantities have size only, in this case the size being 3 meters per second. However, the velocity is different because they're moving in different directions. Now, generally, if it's moving to the right, we say that it's positive, and if it's moving to the left, it's negative, but really it's just one direction, and then the opposite direction is given the negative value. So when it comes to acceleration, if we have a positive value for acceleration, so if A is positive, then that means we are speeding up, we are accelerating. So acceleration generally means that we are increasing in velocity. However, if we get a value of A that is negative, then that actually tells us that the velocity is decreasing, that we're slowing down. And the name we give to that is deceleration or retardation. So if we just look at everything that we've covered so far, we can see that we have scalars on the left hand side and we have vectors on the right hand side. Remember that anything in the blue pen is for higher tier only. So we're going to look at a worked example now. We'll go through some strategies as to how you answer a mathematical question. I'm going to be using acceleration as the example, but the techniques apply to any mathematical question. So for every calculation, you need to follow these 4 steps because these are where the marks are given in the exam. So number 1, write your equation. Then number 2, substitute in the known values. So if you know what the time is, you substitute that into the equation. You always want to double check and make sure that the units are in the unit that you want them to be in. So for example, time's always measured in seconds. So if you're given a time in minutes, then you'll need to change that into seconds first. Once you have your substitutions in, you can then work out the answer and add on a unit at the end if it hasn't already been given. So we have a car that starts at rest and after 10 seconds it has a velocity of 15 meters per second. Calculate the acceleration. So first thing we're going to do is write out the equation. Acceleration is what we're trying to find, so the equation we need is A is equal to V minus U divided by T. So let's see what values we can put in. We know that after 10 seconds the car has a velocity of 15 meters per second, which means 15 is the final velocity. So instead of V, I'm going to write 15. Minus U, so U is initial velocity. We haven't been given a number for initial velocity, but we have been given the value. And that's because we've been told that the car begins at rest. So at rest tells us that the initial velocity is actually 0. It's at rest, it's not moving. Other words that might be used are stationary. So 15 minus 0 divided by the time taken. The time taken is 10 seconds. So we have all our values in. Now we just need to work it out. 15 minus 0 is 15 divided by the 10 seconds gives us 1.5. We do need to add a unit onto that, and since this is acceleration, it's meters per second squared. If you're asked to work out any of the other quantities, the initial or final velocity or the time, I recommend you write the equation as it is, A is equal to V minus U over T, then put in your substitutions and then rearrange it to get the value that you're after. The reason for this is if you have the correct equation and the correct substitutions, you're getting 2 marks. However, if you incorrectly rearrange the equation, you don't get any marks afterwards for putting in your values. So learn the equation as it is, start off with that, put in your values, and then do any rearranging. So now we're going to take a look at how we would describe this motion on a graph. So I have here a distance time graph. Distance is on the y-axis and time is on the x-axis. Now distance is usually measured in meters and the time is usually measured in seconds. So anytime we have a straight line that is at an angle, that tells us that we're moving at a constant speed. In other words, we're covering the same amount of distance in the same amount of time. When we have a perfectly horizontal line, that actually means that the object is stationary, that it's not moving at all, because the distance doesn't change even though the time does. Now the steepness of that line also gives us information about the speed. So if it's a steeper line, it means that the speed is greater, and if it's a shallower line, it means that the speed is less. But as long as it's a straight line, it is a constant speed. Remember that distance is a scalar quantity, meaning that direction isn't important. So as you travel along in a journey, the distance will only ever increase. So you can see here that the distance, as time's going on, the distance is always getting greater. Likewise, for a displacement time graph, we have displacement on the y-axis and we have time on the x-axis. If we have a diagonal line or any straight line that's at an angle, that means that we're moving at a constant velocity. Because remember, displacement is a vector and velocity is the rate of change of displacement. If we have a horizontal line, then we will again be stationary. However, on this graph, we can have a negative gradient. And what that means is that we're moving in the opposite direction, or returning back to where we started. So you could be asked to actually work out what the constant speed or the constant velocity is from these graphs. And to do that, we need to work out the gradient. Now there's a few different ways of working out the gradient, but the most straightforward way of doing it is to say that the gradient is equal to rise over run. Now other ways that might appear is we could say the change in y, so delta y divided by delta x, the change in x. Or you might know it as y2 minus y1 divided by x2 minus x1. So if we have a look at the distance time graph and we wanted to work out the value for the constant speed, then we would pick 2 points along that straight line. Now we want to make sure that they're as far apart as possible, so I will pick the points at the very start and at the very end. And we connect them together by drawing a large triangle. The side of the triangle that is on the vertical side is what we call the rise, and the part of the triangle that's on the x direction is what we call the run. So using the scale that's on the graph, we can work out what the difference is along the y-axis and divide it by the difference along the x-axis, and that gives us the rise over run. Make sure that you do your best to actually draw that onto the graph that you have in the exam to show the examiner where you're getting any values from. Now it's also important to actually state what it is that you're working out, what the gradient is equal to. So in this instance, the gradient tells us what the speed is. So in an exam, we would write speed is equal to the gradient, which is equal to rise over run. Or you might have velocity is equal to the gradient, which is equal to rise over run. And it makes it clear to the examiner that you know what the gradient represents. If we wanted to work out what the units of the gradient were, then we would take the units for the rise and divide that by the units for the run. So in this case, we have distance on the y-axis, so we would have meters divided by the units on the x-axis, which is time. So we have m divided by s, which we would normally write as m/s, meters per second, which is the units for speed. So next we'll have a look at speed time graphs and velocity time graphs. So next up we have speed time graphs and velocity time graphs. Now the shape of these graphs can look very similar, so it's really important that in the exam you pay attention to what quantity is on the axes. So here we have a speed time graph. When we have a diagonal line that is a straight line but it's at an angle, then it tells us that the speed is changing at a constant rate. So we describe that as a constant rate of change of speed. Now if we've got a horizontal line, then that tells us that the speed is not changing at all. So the value of the speed is remaining constant. So just take care not to confuse the horizontal line that we get in a distance time graph, which means the object is stationary, whereas here the horizontal line on a speed time graph means that we're moving at a constant speed. The only time an object will be stationary on a speed time graph is if the graph itself is at 0. So the line needs to be right down at 0 in order for it to be stationary. We can have positive lines and negative lines, and what that tells us is we're either speeding up or we're slowing down. So a positive gradient tells us that the object is speeding up, whereas a negative gradient tells us that the object is slowing down. If we look at a velocity time graph, when we have a diagonal straight line, that tells us that the velocity is changing and that it's changing at a constant rate. Now we've already met a term that we use for the rate of change of velocity, and that is acceleration. So because the line is straight, it means that that acceleration is constant. If we have a horizontal line, then the horizontal line means that we're moving with a constant velocity because the value isn't changing. We could also describe that in terms of acceleration. So if there is no change in the velocity, we can say that there is zero acceleration. If we have a line that has a negative gradient, then we have a constant deceleration, which means that we're slowing down. Now another word that can be used for a deceleration is retardation. Now remember, velocity is a vector, and that a minus value means that we're moving in the opposite direction. So if we were to have a graph where the line went below the x-axis, in other words, the velocity changes to a minus value, then that would tell us that the object has now changed direction. There's one more bit of information we can get from these graphs, and that is we can actually work out how far the object has travelled, what the total distance is or the total displacement is of the object. And to do that, we work out the area under the graph. So for a speed time graph, the area under the graph is equal to the distance, and for a velocity time graph, the area under the graph is equal to the displacement. In an exam, that's usually worth a mark, so make sure you write it down on the page. When we say under the graph, we mean the area between the line itself and the x-axis. So that would be the area shaded here on the graph. In the exam, the best approach to work out the area under the graph would be to break it up into smaller, easily recognisable shapes, like triangles and rectangles. So if I have a look at the velocity time graph, I'm going to split it up into a triangle, a rectangle here in the middle, and then another triangle. Now a tip for the exam is to label this on your graph and then refer to it in your working out. So for example, I'm going to label each area as 1, 2, and 3. So I need to work out the area of this triangle, I need the area of this rectangle, and I need the area of that final triangle as well. So when you put this in your working out, we'll say number 1, we're working out the area of the triangle, and the equation for that is 1/2 times the base times the height. So we would put our numbers in and work out the area of the first section. Then for number 2, we're working out the area of a rectangle. Now a rectangle is just a base times the height, so we would put in our numbers and work out the area of that. And the same for number 3. And that's the area of the triangle. Again, 1/2 times the base times the height. Now if we want to find the total displacement, then that total displacement is the sum of those areas. So we add it all together. So 1 plus 2 plus 3. So usually in the exam, you'll get a mark for stating that the displacement or the distance is equal to the area under the graph. There'll usually be a mark for working out the areas, and then there'll be a mark for adding them all together. Now, some trickier questions might show a velocity time graph where the velocity is negative. So we know that means that it's moving in the opposite direction. If that's the case where we're trying to work out the area underneath the graph, remember it's always between the line and the x-axis. But if you have any minus velocities, then the area between that line and the x-axis will need to be taken away from the area that's above the x-axis. So finally, we'll have a look at the prescribed practical for this unit, which is investigating how the speed of a ball going down a runway is affected by the height of the slope of the runway. So let's talk about variables and the apparatus that we need in order to take these measurements. If we want to investigate how the height of the runway will affect the speed of the ball, then we need to change the height of the runway. So that makes the height of the runway our independent variable. We want to measure the speed of the ball, or rather the average speed of the ball as it travels down. So that's our dependent variable. But we're not actually measuring speed directly. What we're actually measuring is the time taken for the ball to roll down the slope. Now, in order for us to work out the speed, we need to know two things. We need to know the distance between where the ball has started and where the ball finishes, down here at the end. So we need to know that distance, and that'll remain constant throughout. And we also need to know how long it takes for the ball to travel that distance. Now, we can measure the distance by using a meter ruler, and we can measure the time taken by using a stopwatch. To make sure that this is a fair test, we want to make sure that the only variable that we're changing is the height of the slope. So everything else needs to remain constant. We use the same ball bearing, we use the same surface of the slope, we use the same distance of the slope, the same amount of friction. We keep everything else the same. So how do we do the experiment itself? Well, once we've collected all the apparatus, we start off with a small height. So about 5 centimeters or so. We record the length of the slope, the distance that the ball is going to travel through. And then when we're ready, we let go of the ball bearing while starting the timer at the same time. We stop the timer when the ball has reached the end of the runway. Any results that we get, we record them in a table, but to make sure that they're reliable, we need to repeat it. And we'd always recommend to repeat it 3 times so that you can average it. Once you've done that, we can then change the height of the slope, increase it a bit, and repeat the previous steps. So your results should be recorded in a table like this. Remember that each heading should have the units included in it. What we're interested in is the relationship between the height of the slope and the speed, the average speed of the ball bearing. So to truly see the relationship between those, what we can do is plot a graph. And on that graph, we will put our independent variable, that's the height, on the x-axis, and we'll put the speed on the y-axis. Now what we should find is that as we increase the height, then we do in fact increase the speed. However, it's not a straight line. And because it's not a straight line, it means that they are not directly proportional. So as you increase the height of the slope, then the speed of the ball bearing also increases, but not proportionally. So that's it. We've managed to fit quite a lot of information onto the one page here. Just remember that if you're doing the foundation paper, you only need to worry about the information in black pen. You can ignore anything that's in the blue pen. And I hope that you find some of that useful.